Alright, so this video is about how to draw a voltaic and electrolytic cells. First question, what's the difference between a voltaic and electrolytic cells? So a voltaic cells is pretty much a cell that can go by itself, like a battery. It doesn't require you to put energy into it. Electrolytic cells is the one that you have to have a power source. You put in energy into it, electrical energy, in order for it to work. Both of these cells, however, follow the same rules when it comes to drawing it. And the rules are simple. An ox and red cat. So here's a funny picture to help you remember it. See, a red cat and an ox. An ox. What it means is that the anode, an ox, right, the anode side will have oxidation reaction, and the cathode side will have reduction reaction. Second rule is Euleric, which oxidation, O stands for oxidation, is lose, reduction is gain. And last but not least, electron will flow from the anode to the cathode, always. And I stress again that these rules apply to both the voltaic cells and the electrolytic cells. I'm going to delete this here. So how do you draw these cells applying these rules? I'm going to move this, make more space. Okay, so both voltaic cells and electrolytic cells, you will have two sides, which is an anode and a cathode. Now the difference here is that for voltaic cells, you don't need a power source, so I'm just going to connect the anode and the cathode with each other here. Versus the electrolytic cells, you have to draw a power source. So usually I draw a short line and a long line denoting that it is a power source here. Another difference in voltaic cells, you have two buckets of liquid that these metal pieces dip in, and these two buckets has to be connected with something called a salt bridge. So this salt bridge allows for ions to flow through, which then give you a complete circuit. Electrolytic cells, on the other hand, don't need a salt bridge, so you can just put them all in the same bucket. So let's say you have a voltaic cells contain a zinc and a copper. This is a common. The zinc is more reactive, so that means that the zinc is going to be easier to oxidize. So the zinc gonna get oxidized. I'm gonna put the zinc here. Zinc oxidize. Applying the rules of, and then therefore the copper will be reduced. So applying the first rule, an ox and red cat, the anode will be oxidized and then the cathodes will be reduced. So this guy is your cathode. This guy will be your anode. Okay. What if this situation were to apply in the electrolytic cells? Put the zinc here, the copper here. Because you're putting an electrical current into it, you could force the copper to be oxidized, the zinc to be reduced. So this is not spontaneous. You need energy, you need electricity here. But the rules still apply. Because copper is oxidized, it's going to be anode, and the zinc can then be cathode. See what I'm getting at? Alright, so that's the first rule. Alright, the second rule, Euleric. Oxidation is lose, reduction is gain. So that means that zinc is going to be, here we're looking at voltaic cells again. Zinc is oxidized, so it's going to lose electrons. So if I'm going to write the chemical equation for this, zinc is here. It's solid. It's losing electron, right? So it's going to be zinc plus 2 electron. You may ask, okay, how do I know there's 2 electrons? Just look in the charge in your booklet, your data booklet. Reduction is gain. That means on the cathode. Just rewrite it, keep my room. On the cathode, copper is going to gain electron. Copper on this side, the copper side, is going to gain electron. Well, you're not going to make copper into a copper minus, right? So it's not really the copper that's gaining the electron is going to be the copper ion in your solution in this liquid thing, gaining the electron. So you're talking about copper 2+. Sorry, I should say this is aqueous. Gain 2 electron, becoming copper solid. Okay, for electrolytic cells, it's a little bit trickier because it depending on what is in this solution that you have. So I'll talk about it later. So let's just focus on this. So second rule, done. The third rule is that electron is going to flow from the anode, which is here, over to the cathode, which is here. So I can say, okay, electron is flowing this way. And that makes sense. Here, your zinc, lose electron. Those 2 electrons, you're looking at it right here, are going to go up this, over here, got over here, and then this copper 2+ in the solution is going to grab that 2 electron and form copper solid. Now sometimes you have to write a shorthand cells notation, so it's kind of like an abbreviation, in which case you're going to have the anode on the left and the cathode on the right. So you can write zinc solid, becoming zinc aqueous, right? Zinc 2+, right here, this guy, aqueous. And then you're going to put a short line in between. So this one's before, this one's after. And then you're going to put double line like so to separate the 2 buckets, essentially. And on this side, same thing. You're going to go before you have copper 2+, after you have copper solid. So short line to separate before and after. Done. Electrolytic cells. Slightly different story because now your anode and cathode has got to switch around because you force it to happen by giving it an electrical power to drive electron this way. Again, electrons still going from anode to cathode. Rule number 3, flow from anode to cathode, right? So it's going to depending on what metal ion is in this solution. So let's say you have copper sulfate, so CuSO4. CuSO4, when you have it in the liquid, is going to be Cu2+, SO4 2-, right? Now the cathode, even though you're having zinc here, it really doesn't matter what you have here. Because you're forcing the electron to go over here, really, what's in the solution is going to react. So your cathode is going to have copper aqueous, the ion of copper, adding 2 electrons to it to form copper solid. So really what you're seeing is a layer of copper, solid copper, covering this piece of zinc. So then that begs the question, do I have to have zinc here? Does it matter if I have zinc here? No, you could have another piece of copper, or you can have lead, or you can have whatever. Still, what deciding that which electrode getting the copper deposit on it is the direction that you plug this piece of metal into your power source. That makes sense? And then in the anode, the rule I oxidation is lose. So your anodes have oxidation, you still be losing electrons. So this copper piece, solid, is still going to lose electron. So it's going to dissolve essentially into the water, into the solution. Solid becoming copper aqueous plus 2 electron. Sorry, the copper aqueous have to have a charge. Yeah. So how do I draw the shorthand version for this electrolytic cells? Oh, same rule. You're going to have an oxidation sign written on the left and reduction sign written on the right with the double line to separate the cells. So oxidation here is copper. So you're going to have copper solid. Don't forget the state. Before you have copper piece solid. After you have copper aqueous. And reduction before you have copper aqueous. After you have copper solid. Well, you may say, this is silly. Both sides is some kind of copper solution. What's the point of this? Well, there's a process called electroplating, which means that you are plating a thin layer of a precious metal like copper or gold or silver, whatever, on this piece of object by putting in electrical current for that to happen. So that's the point of that.